Let me start the recording and share the screen. Okay, so last class we started talking about arc length and we saw the formula for arc length. And I just wanted to review a little bit of what we saw. So first, we were told that the arc length, let me see, okay, S. So the arc length, so if you have a curve, so you have a curve in R3, and you want to find the length of the curve from A to B. So that's this length over here. So we give that S. So we say, okay, that's going to be S. That's the length of this curve from A to B. And we were told that that's the integral from A to B of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. And one way to maybe remember this formula is, I'm going to suggest two ways of remembering the formula, but one way is to go, let's say, to this point and say, well, how do I determine, if I go an infinitely small step on this curve, how do I determine that length? So let's imagine we go from this point to this point over here. Well, that length, if it's infinitely small, it should have something in the form of dx squared, square root of dx squared plus dy squared plus dz squared, right? So the dx is the small change. You go on this curve an infinitely small amount. The dx is the small change in your x direction. The dy is the small change that you took in your y direction, and the dz is the small change that you took in the z direction. So that gets you from this point to this point, and then you square it and you take the square root to find the length. And you can then rewrite this in terms of dx over dt squared plus dy over dt squared plus dz over dt squared, and then just have a dt outside, right? So if I took this dt and I put it into the square root, I square it, and then it cancels all the dt's on the bottom. So these are the same. Okay, but what is this? Well, this is just what we have over here. It is equal to x prime of t squared plus y prime of t squared plus z prime of t squared square root dt. This was for a small step, but if you want to go from a to b, you just take the integral from a to b, and there's a dt over here. And that's how you can get this formula. So that's one way of thinking of this formula. Another way of thinking of this formula is by saying, well, it's the same thing. S is equal to the integral from a to b of the magnitude of r prime of t, where r is the curve, dt. And if we took s of t to be equal to the integral from a to t of the magnitude of r prime of t dt, then the change of s over time, so ds dt, which is your velocity, how when you change time you get a small change in your s, is going to be equal to the magnitude of r, okay, and this should be u, the magnitude of r prime of t. And so if we remember this formula, that the derivative of s with respect to t is equal, or the velocity, your velocity is equal to taking the derivative of r and taking its magnitude, then we can recover the arc length by just taking the integral of this thing from a to b. Any questions about this? And the reason that your velocity has something to do with the length is, well, you can think about it in terms of at every point, you're given some velocity, you move in that velocity a bit, and now you're another point. You're given another velocity, you move at that speed, you're given another velocity, and that's how you keep moving along this curve. Small velocities, and you move along them at every infinitely small point. And if you add up all those velocities, that will tell you how long it took you to get from A to B, or not exactly how long, but how long the curve is from A to B. Okay. So last time we did this problem with the helix, and it's actually one of the really only type of problems that you'll be given with arc length, because you have these square root of these squares in your integral. So in the integral, you have x prime of t squared, y prime of t squared, and then you take the square root. And if it's anything too complicated, then it would be very hard to integrate this. But you know, if you have cosines and sines, then you can put them together. When you take their square, you get 1. So that's why the helix type of problems are one that appears quite often. Okay, so now that we understand how velocity works, they want us to determine the speed at time t2 for the particle whose position vector is given over here. R of t is equal to t to the cubed so R of t is equal t cubed negative et, negative e to the t, and 4t at t is equal to 2. So first we want to find r prime of t, which is going to be 3t squared, negative e to the t, and 4. Then we want to find r prime of 2, which is going to be 3 times 4, which is 12, negative e to the 2, and 4. And then we take the magnitude of this thing, r prime of 2, and that gives us the square root of 12 squared plus e to the 2 squared plus 4 squared. And whatever that number is, that is your velocity at time 2 for that given position vector. Any questions about this? Okay. And they tell us that it's 14.6 feet per second. Another thing that we can try to do is, well, every parameterization of a curve, right? Different curves have different parameterizations, and those parameterizations, they can have different speeds, right? You can have let's say you can have a line which has something simple, r of t is equal to t, let's say 2t and 1. So this has one speed, but if I take my t and I replace it with 2t, or let's say 2s, so a new parameterization, I will get the same exact curve. So now r of s is going to be 2s, 4s, and 1. This gives you the same curve, which is a line. But, for example, in the first case, r of 1, so r of 1, let's say that this is R1 and this is R2. So R1 of 1 is equal to 1, 2, 1. But R2 of 1 is going to be equal to 2, 4, and 1. So we're moving along this curve twice as fast. And in fact, when you check the velocity, you will see that you're moving along this curve twice as fast, right? We can even try to do it. We can say, okay, what's the velocity of R1? So R1 prime of t is going to be equal to 1, 2, and 0. So the velocity for this curve is always the same. It does not depend on t. So the acceleration will be 0. And R prime of 2 of t is going to be 2 s 2, 4, and 0. So if you wanted to compute the magnitude of R1, you take the velocity, you take the magnitude of R1 of t, or for any t, it doesn't matter because it doesn't depend on t. And it's going to be the square root of 1 squared plus 2 squared, which is going to be the square root of 5. But for the second one, the magnitude or the velocity of R prime 2s is going to be the square root of 4 plus 16, which is going to be the square root of 20. So, so we see that we increased our velocity just by changing the parameterization of the curve. Even though the two curves are the same, their velocities are going to be different. So you're moving along one curve faster than you are moving along the other curve, yeah?
It'd be double, right?
2
times square root of 5.
Sorry, what?
2 times square root of 5. Double this.
Yeah, you're doubling it. And it's because that you doubled the parameterization. Any questions about this? Okay. So that's basically what they try showing you in example 3. If you take the following curve over here, RT, so R of t is equal to t squared sine t and t. They want you to give the different parameterization using the parameter u, and so now you're going to switch this, that t is equal to eu. So anytime you saw t before, you now just plug in eu. So so now R of u, and let's call this R1 the way they do, is going to be e to the u squared, which is e to u, sine e to the u, and e to the u. So we see that it looks like you have a different curve. You actually don't have a different curve. You also have to change the t itself. So before they said t is moving from 3 to 9, but now because that we have this t is equal to eu, then we can say, okay, so what is u in terms of t? U is going to be equal to ln of t. So that means that our first u, let's say u1, is going to be ln of 3. And our second u, ln u2, is going to be ln of 9. And so now we have our new curve. It's given with this parameterization and with these boundaries. So we need to change the boundaries because we just changed the time or the parameterization. And we then also have to go into the curve and change the parameter, but the curve doesn't change. So this isn't changing the curve. Any questions about this? So that being said, we can now start with any curve and try to find the parameterization that gives us that the velocity of the curve is 1 for all of the parameters. So whatever way we initially went along this curve, rearrange it with some function so that now the velocity is always 1. Does that make sense? So here's a picture of what we're trying to do. We start with okay, this is the one where all the velocities are 1. So we see that all the tangent vectors look the same along this curve. And this is a different one where their velocities are varying. So you have different vectors at different points. So we would want to start with something that looks like this and get something that looks like that. So for example, what we were doing before, over here, all the velocities are the square root of 5. That's what all the velocities are. So we would like to be able to change the parameter so that suddenly all the velocities have magnitude 1. And naively, what we can think about is, well, if my original velocity has the square root of 5, what happens if I go to my vector and every time I see t, I just plug in the square root of, let's say, s over the square root of 5. So let's see what happens if we do that. So let me erase some stuff. So now instead of R1 of t, I'm going to have R2 of s, and that's going to be t over the square root of 5, 2t over the square root of 5, and 1. Okay, so let's find the velocity. So R prime 2, not ts. So R prime, and over here we're taking t, s. Okay, t is equal to s over the square root of 5. Okay, t is equal to s over the square root of 5. So R prime of s is going to be equal to 1 over the square root of 5, 2 over the square root of 5, and 0. So what's my magnitude? So my magnitude is, so the magnitude of R prime to s is going to be equal to the square root of 1 over the square root of 5 squared plus 2 over the square root of 5 squared, and then plus 0, which doesn't matter. So this is going to give us the square root of 1 plus 4 over 5, which is going to be 1. Okay, so that makes sense. If your original velocity was the square root of 5 at every point, and you then rewrite your parameterization in terms of your original variable, in a sense, over the square root of 5. So now t is just going to be what happened before, but I'm going to slow down at every point by the square root of 5. So I'm dividing by the square root of 5. Then your current velocity will be 1. And that's what happens. So more formally, what we are going to try to do is we're going to try to say, okay, what is my s of t? Well, we know my s of t is this integral from 0 to t of the magnitude of r prime of u du. That's my s of t. So that's over here. And yeah, this gives you some function in terms of t. So they, for whatever reason, say k. Let's call this gt. You can call it st. And then what you end up doing is you say, okay, I want a new variable s, which is going to be equal to gt. That's how, but I want to now know what, for each place where I saw t, what do I plug in? I plug in t is equal to g inverse of s. And that's going to be your reparameterization. So this over here tells you the arc length up until the point T. And then you take that and you say, okay, I want a new parameter S so that my velocity is always 1. So let me set that equal to my GT, take the inverse, and then that will tell me what function to plug in for T. So going back here, what would that be? So over here, your GT is going to be equal to the square root of 5 times T, right? Because we got for this problem that that the magnitude of r prime of T, we got this is equal to the square root of T. And so if you say, okay, what is my GT? Well, that's my integral from 0 to T of the magnitude of r prime of T dt, or u, u du. And we know what the magnitude is in here, so we can say this is going to be gt of the integral from 0, gt is equal to the integral from 0 to t of the square root of 5, the square root of 5 du, which is equal to the square root of 5 times t. So that's what my gt will be. It will be the square root of 5 times t. Now, in order to find my s, I say, okay, s is equal to gt. Or in other words, t is going to be equal to g inverse of s. Well, what's g inverse over here? It's just going to be 1 over the square root of 5. So this is going to be s over the square root of 5. Right? If I set gt equal to s over here, then I just divide by the square root of 5 and I get t is equal to s over the square root of 5. Okay, and that's how you find your new parameter, which we did. We said, okay, take every time that I saw t, take s over the square root of 5. That's why you got this here and that there. And then we looked at the velocity and we got 1. Any questions about this? Yes.
On the right, the needed g of t equals like that integral that from that first line. What does that say like inside? It's the underlying part. It's the magnitude of r prime.
The magnitude of r prime of u.
Of what? Of u.
Of u.
Okay.
Yeah. Du.
Du.
Yeah. So it's just this integral. So 0 to d magnitude r prime of u du. Any other questions? So this is what we call re-parameterizing a curve. And this is one way of doing it in order to get the velocity to always be 1. So here's another example. They give you r of t is cosine 4t, sine 4t, and 3t. So r of t is equal to cosine 4t, sine 4t, and 3t. And we want to re-parameterize this curve so that our velocity is always 1. So take a couple of minutes and try to do this. Okay, so we want to first set up our GT. Our GT is equal to the integral from 0 to t of the magnitude of r prime of t of u du. Okay, so what is this going to be equal? It's going to be the integral from 0 to t of the square root of 4 sine of t 4t, 4 sine of 4t squared plus 4 cosine of 4t squared plus 3 squared. Yeah, there should be u's here. Okay. So u. So here's u, and dt. So far, any questions? Okay, so what is this equal to? It's equal to the integral from 0 to t of the square root. And like I said before, this sine and this cosine, they're squared, so you can take them out and get 1 for them. So you really get 4 squared plus 4 squared times 1. And you just put those two 4s together. So that's going to be 16. So 16 squared. Sorry, not squared. There's 16. Plus 9. Yeah. It times 1. So okay, so from here you're going to get 16 let's say okay, sorry, 16 times sine of 4u plus 16 of cosine squared of 4u also squared, and then you just take out the 16s, and this is square root plus 9. Okay, so then you take out the 16s, so you get the integral from 0 to t of the square root of 16 times 1 plus 9, which is equal to the integral from 0 to t of the square root of 35, which means that our GT, so GT, 25, which means that our GT is going to be equal to the square root of 25 times t, right? Now, we want GT to be equal to S, or in other words, S is equal to G inverse of, T is equal to G inverse of S. So that tells us that our our T is going to be equal to S over the square root of 25. Yeah, okay, 5, whatever. Okay, does this make sense? Yeah. So when you get one fixed velocity, it's generally very easy to find the inverse, right? You just divide. So we get, S over 5. And you then go and you plug it into your equation. So now we get R of S is going to be equal to cosine of 4s over 5 sine of 4s over 5 and 3s over 5. Yeah, does this make sense? Any questions? No? Yep.
What are the integrals with like respect to dt?
The integrals are respect to du. Did I write dt? Yeah. Yeah. So that's du. All right. Any other questions? Okay. So that, and of course, then you can take the magnitude, take the velocity, and you'll get 1, right? You can just try it out, see what happens, and you should get 1. And we did an example like that, so I'm going to skip that step. But that's how we reparameterize curves in order to make the velocity 1. Get the same curve with the velocity of 1. So let's summarize what we have done so far. We saw the equation of the arc length. S is equal to the integral from a to b, magnitude of r prime of u du. Okay, now you can do t, but okay. We figured out the arc length function, s of t, which just puts a t where b goes. We then said that your velocity, well, what's your velocity? It's the change in the arc length as you change time. So you vary time and you see how your arc length changes. So that's just the derivative of this equation. And by the second fundamental theorem of calculus, we just plug in the t every time we see a u here. So we just get this r prime of t. We then learn how to reparameterize a curve so that the magnitude is always equal to 1 with the new parameterization, but we still get the same original curve. Any questions before we move on? Okay, the next section is about curvature. So we can think of curvature as how much is there a change in your velocity vector, in your tangent vector, as you move along your curve. So let's say you have a line, your curvature will be 0. And in fact, your velocity vector, will always be the same, right? It might be get bigger, but there isn't an actual, it's not like twisting or anything. Versus something like this, where the curvature might be a little larger because you can see over here your velocity vector is going in that direction, but at the end of this whole thing, it's going in this direction. So your velocity vector has been changing, so you have a high curvature. And we can intuit what it means for a curve to have curvature. Something like this has high curvature because, you know, if you went on it, you would feel like when you're on top of it, like you're getting pushed down because of this curvature. And let's say a DNA molecule has curvature too, because it's, you know, a helix or whatever. So in order to define curvature, what we first do is we define the unit tangent vector, which is this vector over here. So we know what our tangent vector for R is. So we have this r a prime of t, and we can say that the unit tangent vector t of t, well, just take that to be r prime of t divided by the magnitude of r prime of t. Okay, so that's step one. We don't want to think about the magnitude of your velocity vector. We want to think about its unit vector. So just on the curve, here's your curve. At each point, you have a different velocity, but they're all unit vectors. This will be your T of t. Any questions so far? Okay, we then define, and this is not a formula that we're going to use, but we define curvature to be the change in that unit vector over the change in ds as you vary yourself along your curve, right? Your s is your little arc length, along your curve. Your ds is a small change. So here you are on your curve, and ds looks something like this. This is your little ds right here, ds. A small change along your curve, which by the way happens to be ds is equal to the square root of dx squared plus dy squared plus dz squared, right? That makes sense. What is your tiny change along your curve? It's your change in every direction, and then by the Pythagorean theorem, you square all of those and you take the square root. Any questions? So your curvature is going to be your change in your tangent vector as you vary your s. So here are your unit tangent vectors, and you want to change your s a little, move along it, and see how much your tangent vector has changed, and that will tell you your curvature, right? If this is a big number, that means that as you change s a little, your unit tangent vectors are moving a lot, and that means you have a lot of curvature. But if this thing is 0, well, that means you're probably on a line. So let's say you're on a line. And here are your unit tangent vectors. So these are your t of t's. Well, then dt over ds is going to be equal to 0 because there is no change in your big T as you vary s. But if you're on a circle, for example, then here are your unit tangent vectors. They look something like this. And as you do move a ds amount on your curve, as you do move a ds amount over here, your dt over ds, so dt over ds does change, right? Because your dt, your big T, is changing as you vary your s. Yes. Yeah, so the equation for big T is just the unit tangent vector. Yeah, just a unit tangent vector. So you take your tangent vector and you divide it by its magnitude and you get the its unit. Any questions? Okay, so just so that we have some time to think about this, this formula will not be used. So it's good for the intuition, but not going to be used. I mean, they have an example of how to apply it. I'm not going to talk about that. This is the only formula from the curvature section, outside of one other thing that I'm going to mention, that is going to be used. This is your curvature. And what is this? It's the magnitude of r prime of t cross r double prime of t, right? So you take your r, you take its derivative, that's your tangent vector. You cross it with the second derivative. Why do you do that? Well, I'll get to that in a second. And then you divide by the magnitude of r prime of t squared. That's the formula. So if someone asks you for the curvature of a curve, this is what you do. This is the formula that you use. Okay, so now the question is, why this formula? What's an intuition that can help us understand this formula? So let me rewrite it over here. K of t is equal to, and note that the formula, the answer that you get is a number. Your curvature is some number. R prime of t cross r double prime of t over the magnitude of r prime of t cubed. Okay, so first the top part with the cross product. So let's imagine that here's your curve. So this is your curve. Your r prime of t is this vector over here. Now, let's imagine that let's imagine that this cross product was 0. So what happens if r prime of t cross r double prime of t is equal to 0, or the magnitude, it doesn't matter, the magnitude is equal to 0. Well, what does that mean? That means that your velocity vector and your acceleration vector, or your second derivative, are going in the same direction, right? They're parallel. That's what it would mean for the cross product to be 0. Well, if that's the case, then you're probably on a line, right? Where this over here is your r prime of t, and this is your r double prime of t. Right? If your cross product is 0, that means that these two vectors are parallel to each other, which means that it would make sense for your curvature to be 0, right? And in fact, it would be. This up here will be 0. And so your curvature would be 0. If, however, they are different, so let's imagine that you're on a circle, and you can check that on a circle, your r primes of t look like this, and your r double primes of t, and we will see this a couple of times throughout the course, look like this. This is r double prime of t. So you have these vectors. This vector looks like this, and then your r double prime looks like this. Well, now your r prime and your r double prime are orthogonal to each other, which means that your cross product is the biggest it's going to get. And in fact, you have some pretty big curvature. There is a big difference between your r prime and your r double prime. And the cross product is very good at capturing that fact, that there is some big difference between where your r prime is now and where it will be later, right? What does your r double prime of t tell you? It tells you where your r prime will end up being. It's the change of your r prime, right? R double prime is the change of your r prime. So if it's completely pointing in a different direction than r prime, it's telling you that in a few seconds, as you vary along this curve, your r prime will be very different than it is now. And that's why the cross product is used to capture curvature. Now, why is it divided by r prime cubed? I cannot give right now great intuition for that. But you know, as long as that's the only part of the formula that you have to remember, if you remember the first part through what I just said, that the cross product is good at capturing curvature, the difference between r prime and r double prime, and then you just remember what goes on the bottom, then you can now capture curvatures. You can tell me if I give you a curve, what the curvature at that curve is, and that's what we will do next class. What do you mean start learning the material? What do you mean start learning the? Oh, when are we going to stop? The last part that's covered is curvature. So curvature. Yeah, so
Tell you about
you'll
that.
get back to me?
I will. I'll email it.
Thank you.
Are we allowed to interact?